In this lecture, we're going to look at line integrals over vector fields that happen to be the gradient of something. So remember that if you have a vector field f, which we think of as being the force at every point, and you have some path c, that the work along c that the force field f does, well, that's what we call this line integral. And the way you compute that is by taking a parameterization for your path, say r of t, and well, you put f in terms of that parameterization, take its dot product with r prime, and then integrate that from, well, say a to b, whatever the bounds are for your parameterization. So our question now is, okay, what if capital F happens to be the gradient of something? And by the way, if a vector field has this property, we say that the vector field is conservative. Well, let's just kind of dig in and see if anything nice happens out of that. You know, this is something we like to do in math sometimes, is to just look at what seems like it might be an important special case. So we have some path C, which is parameterized by r of t, where t is between a and b. We say, okay, well, what I'm supposed to do is to take the integral from a to b of, well, capital F, which in this case is the gradient of little f, dotted with r prime. Now the gradient of f is a vector which consists of, say, the partial of f with respect to x, partial of f with respect to y. And then if it were a three-dimensional one, you'd have another component there. And if r of t, I can think of r of t as being the vector function x of t, y of t, which means that r prime is dx dt, comma, dy dt. And if we do out that dot product, so I get the partial of f with respect to x times dx dt, plus the partial of f with respect to y times dy dt. So that's the dot product. We're going to integrate that whole thing with respect to t. But now, doesn't that expression in the middle look a little bit familiar to you from some stuff we did back when we were looking at derivatives? Well, we have that f is a function of x and y, and x and y are both functions of t, which means that f is sort of secretly a function of t, and in fact this whole term in the middle is just df dt, using the multivariable chain rule. And so we end up with the integral of df dt. Well, of course, the integral of df dt with respect to t is just going to be f. So it's going to be f at the t value b minus f of the t value a. And I'm writing this in this kind of funny way here because remember, f was originally a function of x and y. So how do I turn f into a function of t? Well, r, the parameterization, is what takes t values and converts them into x and y values. So really what I have to write is f of r of b minus f of r of a. And that's saying nothing more than take the end point of your path and plug that into f, take the start point and plug that into f, and then subtract the results. Okay, so putting that all together, we get what we call the fundamental theorem of line integrals. Which says that if your vector field is the gradient of some function little f, well then the line integral of that vector field along some path C is just equal to little f of the end point minus little f of the start point. As usual, there are some sort of niceness conditions that we should really put here. This is true for basically every theorem that you learn in calculus. So, you know, we are kind of assuming things like that little f is nice. Typically, niceness of functions has to do with, you know, continuity or differentiability. And that also that your path C is nice. And for niceness of domains, things like the things you integrate over, like paths or regions in the plane and that kind of thing, well, typically that means something like it's smooth and it's built out of pieces that are, you know, sort of not real weird. In this case, we want maybe, say, a piecewise smooth path. So that means kind of not too many sudden changes in direction. So there are some kind of niceness conditions here in the background, but in any case, this is kind of the upshot of this. Okay, well, let me just run through a quick example. So let's say that your vector field f is the gradient of some function little f where little f of xy is equal to x squared plus 2xy. And let's let C be the path from the point 1, 1 to the point, let's say, 3, 5 along this path. And I'm just going to draw kind of a crazy path. So here's 1, 1, here's 3, 5. There's some random path. Okay, and we want to find the line integral of this vector field along that path. Now, if we were to do this in the way that we did in the previous section, you'd have to start by finding a parameterization for this path. You'd have to say, okay, well, r of t is equal to some stuff. But of course, for a random squiggle that you just draw from one point to another, it's not really practical to parameterize that. But in this case, we're going to be in luck. So I have that little f is this function right here. So for whatever it's worth, capital F is the gradient of little f, which is 2x plus 2y, comma 2x. But in fact, I don't even need to find that. That's true, but sort of not useful for this problem. Because since my vector field is the gradient of something, the fundamental theorem of line integral says that all I have to do is take f of the end point minus f of the start point. So in other words, f of 3, 5 minus f of 1, 1. Well, here's my function f right here. So f of 3, 5 looks like 9 plus 30. And f of 1, 1 is 1 plus 2. And so we get 36. In particular, I never did anything like an integral in this problem. Okay, well, next time we'll talk about some of the consequences of the fundamental theorem of line integrals and look at a few further examples.